Wanted to work through the example, the worksheet of a gravity light. The gravity light seemed like a great idea to replace kerosene lights. It's much safer. In the gravity light, we allow a mass to fall, releasing gravitational potential energy. And through a generator, we turn that light into electromagnetic energy, light energy, by which we can read or do other activities. So this question is about this gravity light. We're told that in the gravity light, we're going to drop the weight, release the gravitational energy by dropping the weight by 2 meters. And we want that dropping of a weight by 2 meters to power our LED light for 20 minutes. So 20 minutes is 1,200 seconds. And then after that 20 minutes, we'd have to lift up the weight again and allow the weight to drop. Again, getting another 20 minutes or 1,200 seconds worth of light from our LED. In the problem specifically, we're told that the amount of light that we want is 0.05 watts per square meter at a distance of 0.8 meters from the light. And we're told that initially, we're going to imagine the generator that turns the energy associated with the falling mass into the energy carried away by the light, that's 100% efficient. We're also told that the LED itself, which is turning electrical energy into light energy, that's also 100% efficient. So that's the best case for this gravity lamp. That would be the ideal case for the gravity lamp, where all the energy, gravitational potential energy that's released by the falling rocks are turned into energy carried off by the light. We lose no energy if the generator is 100% and the LED is 100%. We waste no energy if the generator and LED are 100% efficient. So here's a sketch. Here's a picture of the problem. I'm imagining over here on the left-hand side, the input energy. So this is the gravitational potential energy that's being released as the rocks in the bucket fall. And I'm imagining over here on the right-hand side, this is the energy carried off by the light. It's the light energy. And that's the energy that's output. And we're turning the input energy, gravitational potential energy, into the output energy, the light energy, by the combination of the electrical generator and the LED itself. So the electrical generator is turning the energy associated with motion into electrical energy. The LED is turning the electrical energy into the light energy. And so there's those two steps in this middle ground here that ultimately convert our gravitational potential energy that we start with into our light energy that we end up with. Now, in the first step in this calculation, I'm going to assume that the generator converts motion energy into electrical energy 100% efficiently. And I'm also going to assume that the light emitting diode, LED, converts electrical energy into light energy with 100% efficiency. So this is the ideal case for our gravity light. And so it will be interesting to see how our gravity light works in this ideal case. Then we can visit a more realistic case of more realistic efficiencies for turning the motion energy into electrical energy, turning the electrical energy into light energy. Now I'm going to write down a few numbers that we need for this problem. And here are the numbers. We want to operate the light for 20 minutes. 20 times 60 is 1,200 seconds. So that's the time we're going to run the light for. We want the intensity of the light to be 0.05 watts per square meter. Remember that intensity is the number of joules per unit of time per square meter of area. So this is 0.05 joules per second per square meter, 0.05 watts per square meter. Then we got two other numbers here, two distances. One's related to the input of gravitational potential energy, one's related to the output of the light energy. The H here, that's the height that we drop the rocks from. So that's going to determine the release of gravitational potential energy. And R here, this is the distance that we want this intensity of light from the LED. So that's going to determine the light energy, be involved in the light energy. So we've got to put all these things together to calculate the mass of rocks that we have to drop to produce this intensity of light at this distance from the LED. The basic idea is that we're turning gravitational potential energy into light energy. We're not going to lose any energy, gain any energy. We're just going to 100% perfectly transfer the gravitational potential energy into light energy. And so I'm going to write down an equation to describe that. Simply going to be that the change in gravitational potential energy, delta's the change, GP is the gravitational potential energy, is going to be equal to the change in light energy, the amount of energy that's carried off by the light. Now, you notice I've got a minus sign and a plus sign on the two energies on the two sides of the equation. That's because one is releasing and one is increasing. So one is giving up energy, gravitational potential energy. One is acquiring energy, light energy. And so they're opposite in sign. Now all I've got to do with that key starting point of energy conservation through our gravity light, I just got to fill in what the change in gravitational potential energy is when the mass falls, and I've got to fill in the amount of energy that the light carries off. So I'm going to fill in some details on the left-hand side and the right-hand side. On the left-hand side, the change in gravitational potential energy will be equal to mgh, where m is that mass of rocks that I allow to fall, g is the acceleration of gravity, and h is the distance that the rocks fall. And this is this famous equation for the change in gravitational potential energy when you either raise or you lower a mass by some amount. So that's our equation over here on the left-hand side. And now we want the change in light energy on the right-hand side. Well, I'm going to start with the intensity of light. We've been told we want an intensity of light that is 0.05 watts per square meter. Now, we want that intensity of light over a certain period of time, 1,200 seconds. So if I multiply the intensity by that time interval, this product, IT, is going to have units of joules per square meter. So it's telling us the number of joules per square meter that we need. Now, that light from the LED radiates out uniformly into surrounding space. If we're at 0.8 meters from the LED, then that light is radiating through a 0.8 meter radius surface. And so if we multiply this quantity here in joules per square meter by the surface area of a 0.8 meter sphere, that will tell us the total energy that the LED must be radiating. So I'm going to multiply this by 4 pi r squared. That's the area of a spherical surface. And this particular spherical surface I'm thinking of is one of radius 0.8 meters. And if I multiply this quantity IT in joules per square meter by this surface area here, which is in meters squared, that's going to give me a number of joules. That's the number of joules that are flowing out of the light. And flowing out of the light, leaving the light, and passing through this imaginary spherical surface where we're trying to read a book. And so this is how we calculate the amount of light energy that has to be emitted over this period of time. Now I've constructed this equation. I can use this equation, rearrange this equation to calculate the unknown mass of rocks that I need to drop to create the known amount of light intensity that I need to read. And so that's the next step. Before I do that, I want to change one thing in this equation here. I put in originally the plus or minus sign because I wanted to remind us about the fact that we're giving up gravitational potential energy. So it's decreasing. We're acquiring light energy. It's increasing. So I wanted to stress that fact. What you lose in gravity, you're going to gain in light in terms of the energies. Now, when it comes to plugging in the numbers and finding out the mass of the rocks, I think what I'm going to do is just worry about the size of the gravitational potential energy that is released. And I'm going to worry about the size of the electrical energy that is acquired, size of the light energy that's acquired. And so I'm going to get rid of the signs. I'm going to just think about the sizes. And by doing that, our mass, well, every quantity that we plug in will be positive, and our mass will naturally come out to be positive. If we wanted to keep track of the signs like I started with, you could do that too. If you were going to do that, you would want to make sure that your changing gravitational potential energy is itself as a number negative by putting in an elevation that decreases by 2 meters. So you would plug in minus 2 meters. But to avoid dragging around lots of minus signs and plus signs, I'm just going to be thinking about size here. The size of the gravitational potential energy that gets released is equal, is equal to the size of light energy that gets acquired. So rearranging this equation, M equals IT times 4 pi r squared. Remember, this looks complicated, but it's really just a number of joules of energy. It's carried off by the light. And we just got to divide that by GH. And if I carry out that calculation, I won't feed in all the numbers, but I'm going to, I won't write down all the numbers. I'm going to put in the intensity of light. It's 0.05 watts per square meter. I'm going to put in the time. That's 1200 seconds. 4 pi, that's 12 and a bit. Then I'm going to put in the r squared. The r squared will be 0.8 meters squared. And then I'm going to divide by 9.8 meters per second squared and divide by the height that we dropped the rocks, which was 2 meters. Plug in all those numbers, and I got 24.6 kilograms. So that mass of rocks is a significant mass that we have to let fall by 2 meters. What is 24.6 kilograms? Maybe I'm guessing it's sort of the mass of a medium to large size dog. So it's like lifting up a medium to large dog. And then you're going to let that mass, whether it's a dog or rocks, you're going to let it fall 2 meters. And then, 20 minutes later, you have to do the same thing. You're going to have to lift up this 20.6 kilograms of rocks, and then you're going to let it fall over the next 20 minutes, and then again and again and again. So I think that's okay, reasonable to read by. Every 20 minutes, I've got a break from reading and lift up some rocks, and then I can go back to reading. But this was for a 100% efficient generator, or 100% efficient LED. So let's figure out now how much mass, is obviously going to be more, we have to drop if a generator isn't 100% efficient. LED isn't 100% efficient. And that's the question in part B of the problem. We're going to find the greater mass, I'll call it uppercase M, that we would require if our generator was only 20% efficient. That's actually not atypical. And if our LED was only 50% efficient, that's also not atypical. So these are reasonable numbers for the efficiency of generator, reasonable numbers for the efficiency of an LED. We're going to obviously need a greater mass if the problem was just the LED and it was 50% efficient, then we would need twice as much mass because the LED was 50% efficient. If the generator was only 50% efficient, then again, that would mean that we'd have to use twice as much mass of rocks to counteract that efficiency. The mass that we'll need for the real generator and for the real LED is the mass for the perfect generator and perfect LED. So that's the mass we just calculated, 24.6 kilograms, divided by the efficiency of the generator and divided by the efficiency of the LED. I wrote those efficiencies as epsilons. I put subscripts G and LED for the generator and the LED. And these are the two numbers that we're told. As I say, for example, if the LED is only 50% efficient, by dividing by 50% efficiency, that's 0.5, I'm going to need twice the mass of rocks. And likewise, if we plug in the efficiency of the generator by dividing by the efficiency of the generator, then it's going to increase the mass. So this is how we incorporate the efficiencies. And so we just need to plug in these numbers now. So the efficiency of the generator is 20%. The efficiency of the LED was 50%. That means that overall, we're only 10% efficient in turning the gravity energy into light energy. We've got 20% efficiency of the generator, and then of that, we only get half of that because of the 50% efficiency of the LED. So we are down to 10%. And so I don't need to write out the numbers here. The mass with the perfect generator and the perfect LED, which was 24.6 kilograms, is now going to be 246 kilograms, 10 times heavier. So now this great idea of the gravity light starts to look like, from a practical point of view, not quite such a good idea for a gravity light. We're now going to have to lift up 246 kilograms. So that might be several people, might be 3, 4, 5 people worth of mass to run the LED light so that we can just read for 20 minutes. And so I'm thinking, well, I would have lifted up the medium to large size dog every 20 minutes, but I don't think I'm going to lift up 3, 4, 5 people every 20 minutes just to read my book.